Dear friends, today we will discuss Hamiltonian circuits and paths. In the last video, we discussed about the Eulerian path and Eulerian circuit, and the origin for the Eulerian path and Eulerian circuit is the solution for the problem of the Königsberg island. So, similarly, the Hamilton path comes or discovered by the Hamilton as a solution of a game. So, in 19th century, Sir William Hamilton invented a game called Icosian game. In this game, each vertex is represented by major European cities. So the objective of the game was to find a path that can visit each of the 20 vertices exactly once at the end back at the first city. So the problem was this. So this is the structure, and here each vertex represents a European city and the edges represent the path between them. So the game is we have to start from one city and reaches at the same city, and when we can cross the same city only once. So what the Hamilton done, he convert this particular problem into this graph, and then he gives a particular solution of this problem in this particular graph. So before going to the Hamilton path, first we will discuss what is a Hamilton path and what is a Hamilton circuit. So a Hamilton path in a graph is a path that includes each vertex of a graph once and only once. So if we remember in the case of Eulerian path, we discuss about edges. So Eulerian path is a path which covers every edge only once. And Hamilton path is a path which include each vertex of the graph once and only once. And Hamilton circuit is a circuit that includes each vertex of the graph once and only once. So at the end of the course, the circuit must return to the starting vertex. So what is the basic difference between Euler path and Hamilton path? So in the case of Euler path, we discuss about edges. In the case of Hamilton path, we discuss about the vertices. And the important thing is that in the case of Euler graph, the important is to cover all edges so that no edge should be repeated more than once. In the case of the Hamilton path or circuit, we have to cover all the vertices, and no vertex can be repeated more than once. So in the case of Euler path or Eulerian path and Eulerian circuit, we have a theorem which says if in a graph all the vertices are of even degree, then that graph is a Eulerian circuit, and if there are only two vertices of odd degree, then there will be a Eulerian path. Same type of theorem is required in the case of Hamilton circuit and path also. But there is no such problem exist. There is no such theorem exist actually. So there we have to find the ways in which we can say that particular graph have a Hamilton circuit or path. But that is not very easy. All things depends upon the graphs. So there are two theorems which can help us to check whether a particular graph is a Hamilton graph has a Hamilton path or Hamilton circuit. But these both theorems are the sufficient conditions only for the existence of the Hamilton path or Hamilton circuit. The first theorem is direct theorem. Direct theorem says if G is a simple graph with n vertices and the number of vertices are greater than 3, then this particular graph will have a Hamilton circuit if the degree of every vertex in G is at least n by 2, or we can say the degree of every vertex of G is greater than n by 2. The second one is Orange theorem, which says if G is a simple graph with n vertices and again n is greater than 3, then there is a Hamilton circuit if we take any pair of known adjacent vertices u and v, then the sum of their degree should be greater than equal to n. But the important thing is that these both theorems are sufficient conditions, not the necessary conditions. We can take a example to understand this thing. We have a graph, circular graph C5. Now this circular graph C5 is a Hamilton circuit. We know what is a Hamilton C5. So C5 is simple. It have 5 vertices. 1, 2, 3, 4, 5. So the Hamilton path is simple. Let's suppose we start from here. We go this. These are the same words. So there is a Hamilton circuit. But if we talk about Derrick's theorem says every vertex, the degree of every vertex should be at least n by 2. Here we have 5 vertices. So 5 by 2, it comes to be 2.5, which is approximately 3. But we can see in this particular graph, every vertex has degree 2 only. So Derrick's theorem is the sufficient part of the theorem. It is not necessary. Similarly, we can apply, if we want to apply the Orange theorem, we can see this vertex and this vertex are not adjacent. Here it is degree 2, here it is degree 2, 2 plus 2 is 4, but according to this theorem, degree of u plus v should be greater than or equal to n. So we have not any uh, strong result to check whether a particular graph has a Hamilton circuit or a Hamilton path. Now let's take few examples to discuss about Hamilton path, Hamilton circuits, and Euler path and Euler circuits. Now let us see this particular graph. If we see this particular graph, we can see the degree of each vertex is even. So this graph has a Euler circuit, and obvious no Euler path by the theorem we have studied in the last video. And now what about the Hamilton circuit and Hamilton path? Now let's suppose we start from F. So we go F to A to D, D to G, G to C, C to E, E to B. Now this will be a path, Hamilton path, starting from F, reaching at the point B. And if we go again to F, it will become a Hamilton circuit. So this particular graph has a Euler circuit, no Euler path, has a Hamilton circuit as well as Hamilton path. Now let's come to this particular diagram. Now here we can see the degree of this vertex is 2, degree of this vertex is 2, degree of this vertex is 2, degree of this vertex is 3, and degree of this vertex is 1. So we have 2 vertices of odd degree and all other vertices are of even degree. It means this circuit, this graph has a Eulerian path but no Eulerian circuit. So it's clear it has a no Eulerian circuit, but it has a Eulerian path. We can find the path also. Let's start from D. We go to the A, then we go to the B, then E, then D, and then again C. So each edge is repeated only once. So this is the Eulerian path. So let's see whether these two have Eulerian circuit or not. So for the circuit, it is very clear that we have a vertex of degree 1. Whenever we have a degree of vertex 1, circuit is not possible because circuits are a closed one. So whenever a graph is closed, it means all the vertices should be more than 1. Degree of all the vertices should be more than 1. So clearly from this point C, this particular graph cannot have a Hamilton circuit. Now let us try to find the Hamilton path. Now what about the path? Whether the path exists or not. Let's try to see. Okay. So to check whether it is a Hamilton path or not, let's start from D. Let's start from C. So it's C to D, D to E, E to B, and B to A. Now it is a Hamilton path. Starting point C, end point A, all the vertices are covered. So this graph has a Hamilton path. Now come to this. Now here we can see it is of degree 3. This is of degree 3. This is also degree 3. So neither Eulerian path nor Eulerian circuit. First two things clear. Now we have to check for the Hamilton path and Hamilton circuit. So let's start with from the A. For circuit, we visited A, then D, then C, then B, then E, and then A. So this is circuit. And if we remove this particular A to E, then it will become a circuit. It will become a path. So this particular graph has a Hamilton circuit as well as a Hamilton path. From let's see this particular diagram. Rest you can do. Let's see. Let's do F1. So here it is degree 3, degree 3, degree 3. Three vertices of degree 3, so it's at degree 4. So this is of degree 3, this is of degree 3 again, two vertices of degree 3. Then this vertex is of degree 1, this vertex is of degree 1. So more than two vertices are of odd degree. So neither Euler circuit nor Euler path is possible in this particular graph. Again, if we talk about the circuit, we have a vertex of degree 1, so circuit, Hamilton circuit is also not possible. Now let us try to find whether this has an Hamilton path or not. This circuit does not have any Hamilton path. Let's try to plot 1, 2, because the theorem cannot be applied here. Theorem can be applied only to prove that a particular graph has a Hamilton circuit. It cannot prove whether a particular graph does not have a Hamilton circuit. So let's start from F. We go to the B, B to the A. Let's suppose from A to E, E to D. Now, either we can go to C or we can go to G. If we go to C, then we cannot travel to G. And if we travel to G first, then we cannot travel to C. So this particular graph does not have Hamilton path. So the next is the complete graphs Kn has a Hamilton circuit for n greater than 3. Now let us take a complete graph with 4 vertices. That complete graph will be like this. The graph is a complete in which there is an edge between every 2 vertices. Now we have to prove that in Kn for n greater than equal to 3, there is always a Hamilton circuit. For this particular problem, it is very easy. You can say it go like this, then this, then this, then this, starting from this vertex, reaches at the same vertex. And the same logic can be applied for all type of the complete graphs. The reason is that there are the only reason that there is an edge between any two vertices of the graph. So we can travel through as many edges we can. So this problem you can do in detail yourself. So this is the homework for you. Please plot these graphs in which a graph having Euler and Hamilton circuit both. Euler circuit, neither Euler circuit not Hamilton circuit, having Eulerian circuit but no Hamilton circuit, and vice versa. And similarly, then Euler path and Hamilton path, then Euler path and neither Euler path nor Hamilton path, and then having Euler path but no Hamilton path, or vice versa means having the Hamilton path but no Euler. This is exercise for you.